You asked me to speak on science, mathematics and beauty, and I'm delighted to speak on it, but let me say this, it's not simple. There are some areas here which I'm going to stretch your brains, but I want you to see that mathematics, it really does point to the greatness of Christ. And when any area of science is done properly, it points to Christ. Who was it who said this? I am neither clever, especially clever, nor especially gifted. I'm only very, very curious. Who was that? Anybody know? You are right. Somebody got there first before the others. Albert Einstein said this. And that shows actually, just in that area, a humility, doesn't it? Now, obviously, I'm not saying that he was humble in everything he did, but in that area, he was actually prepared to say, well, let the science tell me what we should understand. He also said this, the most incomprehensible thing about the universe is that it is comprehensible. In other words, he was surprised by the orderliness and the elegance of what he looked at in terms of the stars and the planets and everything that he particularly was looking at. Tonight, we've got a few things we're going to look at. Some will be longer than others. What is abstract thought? Because mathematics, I want to get underneath it, is what we call abstract. That means that it isn't to do with matter and stuff that you can touch or energy that you can see the effect of. It's to do really with coded and cryptically written ideas, isn't it? It's to do with coding, really. And so we do need to understand the idea of what is abstract. That is something that you cannot grasp, and yet it's real. We do need to be aware of that point first. The nature of mathematics, how is it real? The uncanny connections in mathematics go right across the disciplines, and the power and coherence in mathematics, and so on. So you'll see us running through the top right-hand side. You can see that we'll be making our way through that little agenda. So we're going to think, first of all, about the nature of abstract thought. How interesting that C.S. Lewis, no mathematician, but a brilliant mind, both at Oxford and Cambridge, converted from atheism, right? Converted really through God used this logical mind to at least show him that his atheism could not answer everything. Now, I'm not saying that this is always the way to reason with people, but C.S. Lewis's conversion is a very, very important conversion in last century. He said, nature is quite powerless to produce rational thought. What do I mean by rational thought? Well, the idea to make a rational argument, to go from A to B with logic, okay? We're talking about logic. So, nature is quite powerless to produce rational thought. Not that she never modifies our thinking, but at the moment she does so, it ceases for that very reason to be rational. So, if I have a funny tummy, or if I get ill in some way and it begins to affect my mind and I get delirious, I start talking nonsense, and you immediately say, well, it was that coronavirus that he picked up, or whatever it was, that I needed Dick's special machine to clean me up, and then I'd start thinking correctly again. Do you see? So it's these things which show to us, C.S. Lewis is saying, that reason is something which isn't to do with a chemical reason that I'm using these words. It's to do with thought. For as we have seen, a train of thought loses all rational credentials as soon as it can be shown to be wholly the result of non-rational causes. He was a Christian, or became a Christian. J.B.S. Haldane was not a Christian and was never converted as far as I know, but he said something similar. And he was a giant in his day in the chemistry arena. If my mental processes are determined solely by the motions of atoms in my brain, I have no reason to suppose that my beliefs are true. And hence I have no reason for supposing that my brain is composed of atoms, or to be composed of atoms. See? So if you actually follow his logic, he's actually right on this point. And he's being very honest and admitting to the world as it was then, and I wish more people would admit this today, that if you actually reduce everything just to chemistry and physics, then you can't be sure of anything. And that's going to become quite important as I develop this argument. Not all these people, of course, do I agree with on everything else. And please don't think that if I quote a Christian, I'm necessarily agreeing with everything that they say in a different context. But in the main, of course, I agree with C.S. Lewis. He wrote some brilliant books. But, so please don't sort of go away and say, well, Andy quoted this person, therefore everything that person has written is necessarily correct. Obviously, when it's a non-Christian like Haldane, I'm not saying everything he wrote is true. And we need to be aware then that what C.S. Lewis said, which is a very important point, just put that back up again, is that rationality is not the same as chemistry and physics. Please do grasp that. Because this is now showing that the ability to think abstractly is something which transcends matter and physics. That's what I'm getting at. And it's going to lead into what we're saying in a moment about mathematics. It's interesting that John Lennox has actually really grasped this point in his book, God's Undertaker, where he says the whole point about, and he's talking here not about the mind, he's talking about DNA, but it's connected, the same point, that the DNA code is not determined by the chemistry, not necessarily anyway. The whole point about the nucleotide bases, and if you're familiar with DNA, it's got these cross members going across the ladder, the nucleotides, is that they may be positioned essentially randomly if you just sort of left it to jumble. If there were any affinities, that means physics and chemical reasons why they should come together, their information carrying potential would be drastically reduced. So it's the very fact that you could have put them in any way, but they're not. That CAT, cytosine, adenine and thymine, stands for a particular amino acid, and other combinations in triplets stands for yet another amino acid, and so on. And then it builds up a protein. It codes for the proteins. So he is basically saying that there is a similar issue concerning the nature of abstract thought in the nature of abstract coding, right? That's thinking of DNA. So we might ask the question, what does define the information? Well, it's certainly not the DNA molecule. It's not the DNA code itself even. It's not the energy stored in the molecule. It's not the protein, which amazingly makes the DNA. And yet the DNA codes for the protein. There's a chicken and egg problem there. But the DNA information is in none of the above. It is essentially non-material, and it's information which is expressed in the coding, which has a purpose to it, to actually build amino acids and thereby build proteins. So there is quite an overlap here between 2 points: the coding, which we have in biology for the DNA, microbiology, and also this thought about where does the mind come from. And it leads into what I'm thinking about, which is primarily mathematics. The nature of abstract thought, then, just to summarise this point, it is not defined by physics and chemistry, neither is it defined by the brain and firing synapses which are going on in our nerves, which are amazingly carrying all sorts of electricity all through the brain, hugely complicated system. Neither is it defined by the DNA chemicals or by the non-material coding that's going on. Even though it's non-material, it's not that of itself that's defining what abstract thought is. We are not just simply, as Dawkins said, dancing to our DNA. We are far more than that. And that's what I'm getting at. And even before we start talking about the Bible and God, which of course you know full well, and I'm unashamedly going to refer to the Bible, even before we get there, one of the big signposts is the nature of mathematics. This was my first degree. I loved doing applied mathematics. My wife is a pure mathematician. We do talk. I mean, taught not just with letters and diagrams. Please do realise that. But she doesn't really like applied maths. She likes the purer maths. But by the way, the pure maths often suddenly realises that there is an application in applied maths, and there is a lot of, trade-off between the two. Applied maths is closer to physics, closer to engineering, but actually we need it as a tool. I always said to my daughter, look, you can do the queen of the subjects, which is mathematics. The king, of course, is theology. And she went and did medicine. But anyway, I still let her do it. But, my eldest son, Philip, did mathematics, and David is actually also has done mathematics, and he's using it very much, and has done in his PhD. So mathematics goes all the way through the disciplines. It actually goes into the arts as well, as we shall see. So what about the nature of mathematics now? As I've talked about the nature of abstract thought, now I'm talking specifically about mathematics. And now do you see, I'm talking about coding. It's communication with words, but using a very special type of words. It's not material, as we've already been saying. Neither is the message necessarily defined by the code. Right? We use X's, we use Y's, we use equal signs, we use square root signs, and you'll see some of those in a moment. But, I'm going to blind you with some of these equations, but I'll tell you what they mean. Okay, but do you see that the mathematics is actually an expression of a message, but it's a very precise language. If you get one thing wrong, point. Red line through it, 0. Well, not quite 0. Give a little bit for method, but there we go. At least you understand the issue that, as with computer codes, you've got to get it right. It's similar with mathematics. You've got to get it right. I've just put a picture up there that actually the d of whatever it is, in Morse code there, is actually the message, John loves Mary. And I think Mary would prefer to have it written in the sand, or maybe written on a card, rather than having it done by Morse code, which is what's there. What is it? Deep, da, 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 di, 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 and so on. If you look in that box there, it's Morse code. You don't use Morse code anymore. You're looking blank. None of you know what Morse code is. But they did use it in the Second World War, and it was connected with flashing lights and all the rest of it. So logic and mathematics uses logic, and uses obviously logic, and it uses symbols to express it. Pies, like I mentioned, and square root signs. Yet the message can be much more powerful than the words can explain. In the little bit of maths that I know, I've experienced also the sense of eureka when you solve something and you find the answer to something. And you see the amazing way that mathematics, sort of encapsulates an awful lot of reality. And amazingly, when you get it right, doesn't just look at the reality you were looking at, begins to point to other realities that you might consider. That's the power of mathematics, which we're coming to. There is a sense of mathematics suddenly clicking. It's the only way I can put it. Others have said the same. That when you actually concentrate on a problem, you suddenly see that everything is all connected, and you solve this, and then suddenly the whole thing comes into sharp focus as to what you're doing. That is the great benefit of mathematics. And Roger Penrose, actually said these words, I see, eureka, I understand. Let me put the full quote of Roger Penrose, not a Christian. He's really a sort of Platonist in the way he writes. He argues against artificial intelligence, and I believe he's right there, that there is no such thing as an intelligence which will completely mimic the human mind. It will go, obviously we use machines a huge amount. We're using these Steve Jobs machines, which I graded up to from Windows, which, to be frank, I dumped 6 years ago because they just never worked. But, even these ones, they are just they are really only responding to programs earlier that people have written. And even when you go to modern systems today called expert systems, which learn as you go along, Google uses them to predict what you would like to buy, and it makes you buy things you didn't really want. And this sort of thing, that's an expert system. It's learning as you go along. But even those are actually the result of some sort of algorithm somewhere tucked away in Washington, D.C. or wherever it is. So do you see what I'm saying? That these things are not the same. And Roger Penrose realised that. And he was arguing in that book, Emperor's New Mind, that there is something amazing about the human mind. He didn't get as far as saying he was a believer, and I don't think he is yet. But he said this: if I'd been concentrating hard for some while on mathematics and someone would engage me suddenly for conversation, then I would find myself almost unable to speak. And all that happened was that my wife came in to say, do you want a cup of tea? And I've had that experience myself. Yes, she asked me that many times, but what I'm saying is I've had the experience of doing a mathematical problem, not that I'm doing a huge amount of it now. I'm emeritus professor of thermodynamics at the University of Leeds, still connected sort of by a long umbilical cord, but I'm not doing a huge amount of research now. But you can look me up as to what I've done in acoustics and mathematics of ignition and all sorts of things like that. But I've had to concentrate. And then, my whole mind is engaged in that problem. And it's because words are sometimes useless, as he says here, for mathematical thinking. If you're engaged into the mathematics of a problem, you're actually thinking in terms of logical symbols, combining them together, seeing the implications of the logic, and words cannot express it. That's the point he's making. You have to think in terms of you've really got into another world, which is an abstract world. We call it, in layman's terms, particularly for the engineers here, they will perhaps understand the term mathematical modelling. You're making a model of the real reality, and you're saying that the model is so powerful that you can walk into the model and actually use all the mathematical representations of the outside world. And you do it so well, and the mathematics is so robust that it tells you something that you never knew was there. Then you come back to the real world and you say to the physicist, go and find it. And the physicist does find it. I'm coming to that. It is real. Mathematics has a reality. And the very fact that there is mathematics shows to you that you have a mind, which I'm going to say is reflecting the great mind who made you. Do you see? So mathematics itself is a massive pointer to the fact that we are made as transcendent beings. That means that we're not just matter and energy, that we are far more than that. You'll find that many atheists just will not go here because they see the implications. Mathematics is real, and yet it is not defined by matter and energy. So the universe has a third fundamental quantity. I've called it information, but you could call it abstract thought even, that there is an abstract reality which our minds are tapping into. But we're only tapping into a little bit of it. Even the greatest minds, even what we call the polymaths, those are people who can think in all disciplines, usually brilliant at music as well. Even they would say, well, we're only just going into the tip of the iceberg of the reality of abstract thought. Thomas Nagel, who's a very brilliant atheist, he's probably the only honest atheist who has written, in my view. There are other honest atheists, but this atheist is honest. He's still an atheist, but he sees full well that naturalism, which basically means that matter and energy is all that there is, materialist naturalism, leads to reductionist ambitions. That means trying to reduce everything to atoms and just sort of physics and chemistry and electrons and stuff. To reductionist ambitions, because it seems unacceptable to deny the reality of all those familiar things that are not at first glance physical. But if no plausible reduction, that is, if you end up in a cul-de-sac in this thinking, is available, and if denying reality to the mental continues to be acceptable, and he's saying basically that does happen, that suggests that the original premise, which is matter and energy is all that there is, materialist naturalism, is false, and not just around the edges. Perhaps the natural order is not exclusively physical. This comes from the book Mind and Cosmos. Now, some of you here may not be Christians, I think most of you are, but one or two of you may not yet have understood that there is a robust Christian position which shows to us that the science is like a massive signpost telling me that there is a God. I've shared this with other people at the University of Cambridge. I've corresponded with them. I've talked with people. Sometimes, as some of you know, I go and do open-air meetings in Cambridge, and I meet a lot of Cambridge University students, and I try to talk to them on these things, and they just don't get it. They don't see it. They don't want to go there because they see the implications. I tell them to read the book Mind and Cosmos, but still they don't see it. Thomas Nagel does see it, and he's sort of waiting for somebody to resolve it. But actually, you can only resolve it by changing, as he admitted, your premise and saying, well, that there is a God. And that actually matter and energy is not all that there is. There is a non-material reality. And we're not going to be able to use naturalism to explain it. How do you explain that mud led to mathematics over a few billion years? You can have as much time as you want, but matter will not on its own produce logic. That is the issue. Logic transcends matter and energy because mathematics is an expression of logic. How about this gentleman? I don't think he was a Christian. He was a Hungarian, brilliant Nobel laureate, and he won the prize for mathematics in his day. He's the brother-in-law of Paul Dirac, who you may have heard of, is famous in quantum mechanics. The miracle, he says, of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift we neither understand nor deserve. We should be grateful for it and hope that it will remain valid in future research and that it will extend for better or for worse to our pleasure, even though perhaps also to our bafflement, to wide branches of learning. We're considering now the uncanny connections across disciplines. And I want to explore this with you. I'm going to get a little bit detailed here. I don't apologise for it, because if I'm going to talk about mathematics, I'm going to have to put some mathematics up. And I think some of you, and most of you, will actually enjoy it, because I'll explain it as we go along. Let me start with some fundamental constants. 3 fundamental constants in many disciplines, and there are many more, right? Huge number more. Let's do with this one. This is the differential sign. This is when you work out the gradient of a function, right? It happens to be the exponential function, which really rockets up as soon as you increase x, it goes bananas. But when you actually differentiate it, that's why the gradient of it is the same function, right? Now, the natural logarithm is a number which all mathematicians, physicists and engineers all know about. All the people working in physics and astronomy and NASA and sending rockets to the moon and all that, you've always got to have some basic knowledge of mathematics. And the natural logarithm is this number e, which is not a number that anybody normally recites to his wife as he gets up in the morning. If he does, he'll get a very funny look. But 2.71828 is the natural base for the logarithms, and it's used in the reverse for exponentials. So you've got e. Now come to something else which is less esoteric, but something that actually I'm sure you're very familiar with. You're always using it. Cars have wheels which go round, okay? You've got a round wheel. And a wheel is a circle. It's almost a circle, obviously, if it's flat a bit and as it hits the road and all the rest of it. But basically a wheel has, or a circle has a distance across, which we call the diameter, and the distance going round is the circumference. And you know that the circumference divided by the diameter is always, without fail, what? Pi. Not the pi that you ate today, which was lovely, but the symbol pi, which of course is 3.141592653 and all the rest of it. And you can carry on, and people have competitions, I don't know why on earth they do it, to recite pi because it's got an endless set of numbers, just like E has as well. These are numbers which actually you could never actually totally define. They're irrational in that sense. And then there is another number, but it's not a number, and yet it is a number, and yet it's not really a number, and yet it's talking about something outside of our real numbers. And it's something you think, well, what on earth does this mean? You can't square root a negative number. We all know you can't do that. But who says you can't? Says the mathematician. Let's suppose that you can. And let's suppose that the unit of the square root of a negative number is, we'll call it I, standing for imaginary. So you've got real numbers and you've got now imaginary numbers. And the mathematicians, the pure mathematicians, love doing this sort of thing. Just playing around, just see what happens. See, I've got a whole new bag of tools now, I'll toss them up and I'll try and see whether they form patterns. That's what pure mathematicians do. They waste time. No, they don't waste time. My wife would tell me off for that. But they love it, Well, actually, would you believe it, that a chap called Euler realised that there was a connection between these numbers? And he said, e to the I pi, which happens to be, no, I'm getting complicated, but it actually ends up being -1. Because, I'm sorry to have to put this up, but e to the ix, some of you may know, and I know I'm stretching you here, so don't worry, I'm going to come down to earth in a minute. But some of you won't really grasp this, but please don't think that in any way you're less of a person because you've been an expert in some other area, right? But those of us who are engineers and mathematicians know that we have to deal with this I business because actually, believe it or not, don't tell the pure mathematicians this, but it's jolly useful. This idea of using an imaginary number suddenly becomes extremely useful. Not that the people who invented I thought that it was going to be useful. They were just playing. But people who are dealing with cyclic behaviour like revolving engines, RB211s, Rolls-Royce is always doing with this. Anything which is cyclic, which is going round and round and round and round, has a frequency, okay? And when you do all the mathematics of this, you find that frequency is connected with this imaginary bit, okay? And then you've got the danger that something may go round and round and then go out of control. That is to do with the real bit when it's positive. And you want all those things, we call it stability theory, you want those things to decay, not to get out of control. So you want the real bit to be negative. So please don't think that you've got to understand all this, but I just want you to see that in the mathematical world, amazingly, the Egyptians never knew about I. They didn't know about pi. That there is a connection between e, pi, and the square root of -1. Why on earth is that true? And many people are puzzled about that. And I think it's to do with something I'm going to quote a bit later, which is that some scientists have this sense that they're tapping into God's thoughts after he has spoken. In other words, God has made even abstract thoughts, when it's done properly, to actually hang together and to actually work across a number of disciplines. It's the only way I can put it. It really is quite incredible. It's uncanny. Let me now come to some other things. Surds, I'll define them in a minute. I've just referred to complex numbers. Non-integers exist, even though their precise value is recurring to infinity. We've just had that with pi, but you can have it, for instance, with square root of 2. And by the way, pi, if you really want it into a number of decimal places, you can say that before you have your cornflakes at breakfast. See whether you can manage to memorise it all. Some polymaths and some people who have got amazing brains have been able to do it to 100 and even 1,000 decimal places. Much good will it do them? But there we go. Now, let me just mention something else. Some of you, probably about half of you, may remember that if you're going to solve a quadratic equation, there's a formula, do you remember? Yeah. You were taught it when you were in your nappies doing maths at school. And, you know that it's x equals minus b plus or minus the square root of b squared minus 4ac all over 2a, right? Well, you think, what on earth do I have to learn that for? Why? Because it occurs right across all the disciplines: physics, chemistry, biology, space travel, everything. If you don't know how to solve a quadratic equation, you won't get very far in the disciplines these days. There is actually a formula, even for doing it for cubics, but it's pretty hard. And occasionally people have done that. So, you see, even in the complex solutions bit, which sometimes occur when b squared is less than 4ac, right? You get all sorts of possibilities, which are now, and I won't go into the detail, but I've already referred to it, that if you're dealing with what we call stability theory, and it really does apply when you've got real practical situations where you want to make sure that that engine's going to be stable, right, in some particular environment or some situation where you'd have a real catastrophic failure if you didn't make sure that things were going to be stable. I've had it in my discipline of ignition, looking at the ignition of certain combustible substances, the danger that they might appear to be safe, but suddenly the temperature will go up and you go into a fire situation. So it's that sort of area where it occurs. But there are connections also of geometry and key ratios. One example is the golden ratio. I think you'll like this. If you've not followed the last two slides, don't worry. But this is interesting. Fibonacci, who had nothing to do except just sort of count all day, realised that actually, no, he was a bit better than that, but he was, as the name suggests, a brilliant Italian. He realised that actually there are some series of numbers which are interesting. If you start with 0 and 1 and you add them together, you get 1. If you add 1 and 1 together, you get 2. You're reading well. But now if I was to take that off the board, would you still be able to do it? It gets harder now. If you add 1 and 2 together, what do you get? You're doing well. Oh, it's not all of you are quite sure. Now, if you add 2 and 3 together, what do you get? And so it goes on. You go 8, 13, 21, 34, and the numbers are doing odd things. They're getting huge, and they're missing whole lots of other numbers. Strange, isn't it? But people have looked at this, and they said, well, the nth number divided into the n plus 1th number is actually heading towards a constant, which amazingly is 0.618. So the ratio of the numbers tends to what we call a golden ratio, which is 1.618. It's actually 1.618033 and so on. But we won't worry too much about that. Interestingly, the inverse, which we call small phi, is 0.618 and the same numbers. It has that property. Now, there's some interesting things going on here, because now if we actually look at some applications of this golden ratio, suppose, and pure mathematicians love the word suppose, right? We're going to go into something which might seem totally unreal. Supposing the ratio of the smaller part to the larger part in a line, which you're going to break at some point, is the same as the ratio of the larger part to the whole. So we split the number. So the smaller part to the larger part, okay, is the same as the ratio of the larger part to the whole. So we need to try and express that. What is the ratio of the larger part to the whole? Well, if the larger part is B and the total is A, then the larger part to the whole has got to be A minus B to B. You understand? You look completely lost. Admit it. Right. Ice cream is not coming soon, but some lovely cake, which will really put you to sleep. Okay. But the ratio of the smaller part to the larger then is A minus B over B. I think most of you are seeing this. Now, because B over A is phi, we've got the word substitute. We put B equals A phi at least in the top one, and you get that, okay? And you now realise that you're saying that B over A is equal to that. Well, you've just got B over A's everywhere. And if you put this B over A over there, right? We've actually got that, of course. So if you put B over A over there, that means you've got phi squared is equal to 1 minus phi. Quadratic formula! Minus B plus or minus the square root of B squared minus 4AC all over 2A. All comes out to be root 5 minus 1, which is the golden ratio, 0.618 or thereabouts. And 1 over phi, as I said, is 1.618 labelled phi. Now, so we actually know that this golden ratio can be formed by splitting a line. Now, supposing we actually put B across the top as well, right? So we form a square, which is to do with this ratio because we split the line first, okay? So we know where this breakpoint is coming. So now we've got B there and B there. Okay, now if we keep on doing that, we start doing it to this one as well, in the same ratio, we get this type of thing happening, right? So we started off with this, which is B and A minus B, and it was B against A. And now we're actually, there's B and A, and we split it in the golden ratio. Now we split this in the golden ratio, split that in the golden ratio. And now we join the points, right, where this division is taking place, and we get an interesting spiral. That is called the Fibonacci, or the golden ratio spiral. And the golden ratios also can be used with angles, such that the circumference, right, B over A is 0.618, or the inverse 1.618. And if you do that, then there is a golden angle, which is 137.5, and the outer angle here is, of course, 360 minus that, which is 222.5. You say, what on earth are you doing all that for? Pure mathematics, having a nice little fun time. Then you go out to the real world and you find the patterns exist. Not always, it's not always exact. Nobody's saying that, all beauty, by the way, can be connected with the golden ratio. I've read some articles, trying to dish this whole idea. And frankly, they're just going over the top. And we have to be careful that we don't go over the top. We're not saying all beauty is necessarily connected with the golden ratio. But nevertheless, there's an awful lot of natural things which are following this golden ratio. The angle between successive florets in some flowers is the golden angle. So as you can see here, it's saying that this one grows, then that one grows, then that one grows, then this one grows, then that one grows, you see? So it's always going round in this way. That's in the way it grows. I love, not that I can eat them easily because I'm getting old and somehow it does something funny to my insides, but I love it when Juliet gets a pineapple from the supermarket and I say, is it a Fibonacci pineapple? And amazingly, they usually are. because there are spirals coming down here, right? You can see the spirals here, okay? And then you see spirals going the other way. Palm trees also have these spirals. Lots of things. Pine cones have these spirals. If you look here on the sunflower, there's sunflowers, but here you can see that the number of spirals, and I pointed them out for you here, this is the ones going like that, then you've got other ones going like this, and then actually you've got a third set of spirals. You usually can see a third set as well. And they are always Fibonacci numbers, amazingly. Basically all pineapples, all sunflower seeds, all pine cones, and all these things which are growing naturally will have Fibonacci numbers in them. The number of spirals is invariably a pair or triplet of Fibonacci numbers, 21, 34, and 55 in the ones that I've used there. And the golden ratio constantly occurs naturally in the world out there, the growing world, the natural world. And of course, the demonstration of the Fibonacci series and the golden ratio is actually quite evident in other areas as well, as this little video is tracking. You've got things like the Parthenon and others in Greece. And of course, it's all to do with this formula that I mentioned earlier. And you'll find actually that the Nautilus shell and even the ammonites fossilized not millions of years ago, but just a few thousand years ago in the flood, also show this capacity. There's a lot of things which show that the golden ratio is being used in the natural world, and as I indicated, the Parthenon in Greece also shows this with the amazing architecture which it displays there. So you should be aware that there is in art many painters which have used this. Leonardo da Vinci has used the golden ratio. It's not that you have to use the golden ratio in art to do it, but it is very striking that it's quite common for artists to do it. Some architects, like the Egyptians, certainly used the golden ratio in the pyramids, like the one at Giza. You can actually find that if you call this distance 1, you'll find that this distance is 2, but this distance is 1.618. And that distance, therefore, becomes the root of 1.618. So it's actually being used in the construction of the Egyptian pyramids. A particularly beautiful example of the golden ratio, particularly bearing in mind that Charles Darwin said, "A small trifling particulars of a structure often make me feel uncomfortable. The sight of a feather in a peacock's tail, whenever I gaze at it, makes me sick." Okay, well, let me just, if Charles Darwin was here, make him feel a little bit more sick. Because did you know that the beauty of the eye of a peacock feather is actually linked with the golden ratio? The ratio of the two lengths here is it's not always exact, but it's certainly in the region of 1.6, 1.61. And this distance actually is very pleasing to the eye. It looks like an eye. It's the eye of the peacock tail. It's a cardioid, which is a mathematical symbol in its own right. This thing here is a cardioid. And it's an amazing feature, and it's all done by, of course, the light hitting the feather and actually reflecting slightly differently at one surface to the surface underneath. It's an iridescence. And all these individual barbs have actually got to grow through that image, so that feather is constantly changing the position where it starts and finishes as the barb grows. It's really quite amazing what's going on. Even in music, did you know that it's actually quite common that Fibonacci numbers are used? Bach deliberately used the golden ratio in some of his compositions. And an artist will often naturally put something off-centre, roughly, in the ratio of the golden ratio. He won't really want to put it right in the middle. That's boring. He wants to make it look a little bit interesting, and that's often done. Did you know that music is full of the golden ratio and full of the Fibonacci numbers. When pianos was first used in the Western world, the basic frequency was 440 for A, and then C would be 6/5, which would be 528. This is the frequency. And then there would be 5s and 4s, 4s and 3s, 8s, 5s. These are all Fibonacci numbers. And these are what we call the minor third, fourth, fifth, augmented fifth, and sixth, and so on. So all the time, when music came in initially, it was using the Fibonacci numbers. The problem is that you couldn't transpose easily to a different key. So in later years, the equally tempered frequency was introduced, where it's not exactly the same as those numbers, but very close. And now that meant that you could easily transpose from one key to another. Otherwise, you were locked into playing in C all the time, or A, or whatever it was that your harpsichord was tuned to. Do you understand? It's all in the book. So Kepler said this: geometry has two great treasures. One, the theorem of Pythagoras. The other, the division of a line into extreme and mean ratio. The first we may compare to a measure of gold. The second we may name a precious jewel. Just a few other tidbits for you. Did you know that 1 times 8 plus 1 is 9? 12 times 8 plus 2 is 98? 123 times 8 plus 3 is 987, and so on and so forth. You see amazing patterns developing. This is, of course, because you're using the base 10. But because the base is sort of the basic counting that we're using, we could have used a binary system and you'd still get patterns developing. But it is interesting to see that there are uncanny symmetries going on. Did you know that 1 times 1 is 1? Well, that's no big deal, is it? Did you know 11 times 11 is 121? Did you know that 111 times 111 is 1, 2, 3, 2, 1? And so it goes on. Quite amazing, isn't it? So you get some amazing things. Now I'm going to blow your mind, because you're going to say, oh no. Well, just a minute. I'm going to put up another equation. Some examples of differential equations. This you won't understand, and most of you won't, but that you do have to sometimes solve some pretty nasty equations, which are to do with, you remember I said differentiate means the gradient. Now you're differentiating twice, and you're adding it to another differential. I won't go into all the details. But we find that these are equations which keep on cropping up. That the double derivative with a distance is equal to naught. We call that the diffusion equation, or the Laplace equation. It doesn't just occur in my subject in heat. It occurs in aerodynamics, not thinking of heat at all, low speed flow. It occurs in electromagnetism. It occurs everywhere. So we know it's a ubiquitous equation. Another equation is the wave equation, that something is bouncing around and it bounces back again. On this particular one it does. And it could be to do with water waves, it could be to do with sound, it could be to do with light, it could be radio, it could be electromagnetism, it could be water. My point here is that these equations occur everywhere. They're ubiquitous right across all the disciplines. Einstein said, how is it possible that mathematics, a product of human thought that is independent of experience, fits so excellently the objects of physical reality? So mathematics unlocks the principles behind the universe. And Kepler said, I was merely thinking God's thoughts after him, and that's the right attitude. That really is the attitude that we should have. We should be humble. It's actually showing to us that there is a mind behind the universe. 2 examples, which I'm now going to, this is the maximum that I'm going to do tonight in terms of complexity. And even this, I'm not going to bother to explain it all. But I do just want to make a point. Mathematics done well has predictive abilities. And this is really amazing. Dirac, whom I mentioned earlier, worked in quantum mechanics. I've worked a bit in boundary layer theory, and I'm just going to show you something of that. This is Dirac's equation. Oh, do you say that's so complicated? This has got a little bit of what I was sharing earlier, differentiating twice with distance, but it's also got this. So it's a wave equation. It's actually Schrodinger's equation, it's called, but it's got an energy and momentum in it. It's all to do with the fact that it's got this Planck's constant in there. It's to do with quantum mechanics. And it predicts 4 solutions as 2 paired solutions. It's to do with the Hadron Collider and all that sort of stuff, okay? If you want really, that's where it really comes in. But this is way ago, this is not to do with their present work. But when it was first done, it was momentous. Because the mathematics that Dirac was solving said there's not just two states for an electron. You've got the opposite possibility, a positron, a positively charged electron. You don't often come across these. You know, I don't sort of see them every day as I'm cycling down the road. But there are such things. At least that's what the maths said. But people said, no, there can't be such things. We've never seen them. We've looked at them. And Dirac said, you need to go and find them. Oh, guess what? They looked and they found them. That is the power of mathematics. Do you see what I'm saying? The mathematics said in the model, remember I said you dive into a model, you forget about the outside world. You say, Eureka, there's something here that I haven't seen before. Then you come back into the outside world and they think you're nuts. But actually, you're right, because the model is, in a sense, more powerful than the present reality. Schrödinger realised, and he wasn't a Christian, he says, I'm very astonished that the scientific picture of the real world around me is very deficient. It gives a lot of factual information, puts all of our experience in a magnificently consistent order, but it is ghastly silent about all and sundry. And then he goes on to say, it cannot tell us a word about red and blue, bitter and sweet, physical pain, physical delight. It knows nothing of beautiful and ugly, good or bad, God and eternity. I'm moving into another area, and I'm coming onto it, which is beauty. And he was aware that there's something missing even in the best mathematics. And yet mathematics is consistent. Schrödinger was a brilliant man. He had that equation which I refer to. Boltzmann, you may have heard of him. He was a sad case, but brilliant. He committed suicide. He was a brilliant Austrian mathematician. He said, philosophy gets on my nerves. If we analyse the ultimate ground of everything, then everything finally falls into nothingness. In my view, all salvation for philosophy may be expected to come from Darwin's theory. In other words, his mind was saying one thing, and yet everything was telling him around him, oh, you've got to be a materialist, you've got to believe in Darwinism. He committed suicide. He was brilliant in the area of thermodynamics, which is my subject. And there's his formula there, S equals K log W, which I won't go into here. But that is very much connected with classical thermodynamics. But he couldn't see his way out into what his experience told him, like Schrödinger, that there is something beyond us. And he was refusing to obey the signpost of the maths, basically. Prandtl. Now, I'm serious here, I don't want you to try and understand all that. But I do want you to just look at the picture up there. You all know that when an aircraft goes through the air goes over the wing. Good job too. The last time you flew in the A380, the air was going over the A380 wing, and it was following a different path to the air underneath, and the air was bending, which gave lift to the A380, right? Doesn't matter what aircraft you're flying, it's the same with the Cessna. In fact, you could have a flat plate, which is what I'm showing there. And we have things which are called boundary layers. For a long while, boundary layers were a real problem to understand. Then along came a very clever system which broke up the flow into two areas. We talked about the free stream And then we talked about the boundary layer equations. It gets jolly complicated. In other words, you split the area into two. I've constantly had to do that type of thing with my work in combustion. My papers are full of equations, okay? I'm constantly having to match two bits. And when you do the matching, hey presto, something remarkable happens. You suddenly find that you actually get a feel for how thick this boundary layer is. Whether it be in airflow, whether it be in combustion, and it tells you something about the physics. It's just an illustration. I'm not asking you to understand it, but it's like a jigsaw. There is a similarity to the same deep sense of pattern and aesthetics that you get in music, right? There is a strong connection between mathematics and music. When you do things properly, you get a profound sense of achievement. I did it. No, well, you shouldn't really be saying that. But you should be saying, it clicks. I know. I understand. And this musical connection is very much what really is going on in the minds of people who are doing the maths properly. They are seeing the music of, as Einstein referred to, the music of the spheres. He understood the connections. And that, I believe, is what we should be doing in our mathematics. The power and coherence of the mathematics is such that when you get it right, the mathematical models have great predictive power. They are beautiful, they are elegant, and they predict things, which is what I've been saying already, but I'm going to illustrate further with Newton. Just very simply, I'm going to put up some equations. These ones you may well know. Have you heard of Newtonian gravitation? NASA had to actually work out what the pull of the sun would be, not only on the Earth, but on the satellite or on the Apollo spacecraft as it was going to the moon. They had to take account of all these things. And of course, all of it was to do with Newton's theory of gravitation, which has been proved wonderfully true. Kepler found, and he was a great Christian gentleman, he understood the planetary motions of all the planets going around the sun, and he could predict the period of Venus, how long it would take to go around the sun, even in an elliptical orbit, because he said that the area swept out would always be the same in a particular unit of time. That's what that formula is saying. Einstein brilliantly found that the energy of mass, when it's changed into energy, will obey the formula that the mass times the speed of light squared, which is a phenomenally large number. And of course it led to people using it for the wrong reasons, as you well know, with the atomic bomb. The one which really, I think, takes the biscuit, though, is someone that Einstein looked up to. James Clerk Maxwell. Brilliant Christian gentleman from Scotland, who spent his last 8 years at Cambridge at the Cavendish Laboratory, on which are written the words, the works of the Lord are great, sought out of all them that have pleasure therein. He was unashamedly a believer. Would you believe it? He took the 4 equations which were then known about electricity and magnetism, and in particular these last 2, he was able to predict what would happen with the speed of light. He said that light is an electromagnetic wave just by thinking about the physics and the mathematics. He knew that if you propose that the electric field is at right angles to the magnetic field, then those same equations would predict that there was a wave. And he found what the wave equation was. And he found that the wave equation, which is written there, would have a speed, and it would be related to the permittivity of free space and also the magnetic permeability of free space. Just 2 numbers. And they are measurable. You can actually measure the electrical permission, as it were, of free space, how much an electric field can be generated in empty space by a given charge, how many coulombs, whatever you've got. The magnetic permeability of free space, that can also be measured. Using those 2 numbers alone, he could predict what the speed of light would be. Nobody had ever measured it. It's roughly 300,000 meters per second. People came along and measured it, and they proved that Maxwell was exactly right. He did all his work before he died at 49. He is probably the most brilliant scientist ever. Einstein looked up to him, said, without Maxwell, he wouldn't have been able to do his theory of relativity, and it's true. The power of mathematical prediction is really at its apex with Maxwell. Maxwell was the person for physics. Without Maxwell, everything would not have flown. The beauty, elegance, and simplicity of mathematics is its great predictive power, and done correctly, it has elegance, as I've already said, and beauty. Back to Penrose, he said, a beautiful idea has a much greater chance of being a correct idea than an ugly one. Let me draw things to a close. You know this gentleman, Dawkins. The universe we observe has precisely the properties we should expect if there is a bottom. No design, no purpose, no evil, no good, nothing but blind, pitiless indifference. When a friend of mine, and a friend of Matthew Seymour here, approached Richard Dawkins on that lovely wide street where an open-air meeting was being held in Oxford, a friend of mine happened to see Richard and said to him, would you like to read this? An argument ensued. In fact, I think he went away and came back again. And I think it was in the second engagement that he said these words, my brain is just a lump of meat. You can hear Schindler's List going on in the background. This is just awful. Because an atheist cannot even explain his own mind. And it leads to disastrous consequences when you follow that logic. Many people have taken Darwinism to its limit. Evolutionary naturalism, Nagel said, provides an account of our capacities that undermines their reliability and in so doing undermines itself. You see, after Darwin came Nietzsche. Nietzsche said, and by the way, Nietzsche wasn't actually saying, I'm an atheist. You need to be aware that Nietzsche was basically saying, you need to see the logical conclusion of where you're going. God is dead. God remains dead and we have killed him. Yet his shadow still looms. And basically he was saying, you haven't answered the basic reality. He was doing a Nagel, really, in his day. He wasn't a Christian. But neither was he really saying that atheism is the answer. He's basically expressing frustration that the philosophies were not answering the big questions of life. But anyway, he said, of course, God is dead, Nietzsche. But later on in 1900, somebody wrote this, Nietzsche is dead, God. You see, atheistic naturalism with mathematics does just not work, as Boltzmann was seeing in his day. You see, mud to mathematics cannot explain anything. If you try to say that it was done by evolution, where do you get beauty from? And there is lots of beauty and elegance in the mathematics itself. The information that I talked about in the DNA, Einstein's equation, which is so simple and yet so profound, Maxwell's equations and their brilliant prediction of the nature of light. Let me use an illustration. Supposing I hear this beautiful music of Chopin, and I say, well, I don't believe in Chopin. How are you going to explain the information of the music? How are you going to explain that this music somehow made itself? and yet you know that beauty is real. Nothing makes sense unless you say that an ultimate reality is revealing himself not only in the matter and energy which is well ordered, not only in the DNA, but in the aesthetics of mathematics and, by the way, in the aesthetics of music, which, by the way, he loves. Psalm 100 verse 3 says, "Know you that the Lord, he is God. It is he that has made us, and not we ourselves." We need to come back to what the good book has said years ago. That there is an answer, just as the Bible says, in the beginning was the Logos. The Word, the logical principle behind everything. And of course, it's the Lord Jesus Christ. All things were made by him, and without him was not anything made that was made. All things, including mind, beauty, and science. We need to come back to that, friends. My conclusion is pretty obvious. That the nature of mathematical ability implies strongly a transcendent God. We are made in his image. We are a reflection of his own transcendence, and beauty is an expression of our being made in his image. Mud, left for 13.7 billion years, cannot produce logic, mathematics, and beauty, and time will never help. The conclusion? Man is made in the image of a transcendent God. This gives the basis for rationality. This gives the basis for beauty. But I need to remind you that according to the very book that I've quoted in John, this God is holy. And his beauty and his holiness are connected. And supremely, his expression of God was in his Son, the Lord Jesus Christ, who in his own person demonstrated not whatever height he was, not whatever image of his eyes, we're never told, we're not even told the colour of his hair, but we're told of his beauty of character, the marvellous way he showed his love, even for those who stood against him. And the greatest thing of all, Isaiah says, he's as the root out of a dry ground, and we esteemed him not. And it says, it's basically looking to the fact that Jesus would eventually die on a cross, which was very ugly. And the Bible says, because we've rebelled against that wonderful Son of God, the wonderful God who has made us, because we have sinned, that Jesus Christ, the Word of God, became flesh that we might be forgiven. And he died that we might be right with him. I think the science wonderfully fits with what the Bible has always said, that God is the one who made everything, including mathematics, believe it or not. Thank you.